Our universe is 13 billion years old. Everything indicates that in the past it was different. The primordial universe was hot and dense, with all matter compacted into a small space. Today it is large, cold, and with matter spread out over a vast region. And the key to understanding how the hot primordial universe became what it is today is the expansion of the universe. It is actually expanding, and every second there is indeed more space than there was the second before. But at what speed is the universe expanding? The answer is that we don't know. Our experimental measurements of the rate of the universe's expansion do not agree with each other. And what started as a small disagreement in 2013 with the new measurements from the Planck Space Observatory is now a difference of more than 10% and is causing a crisis in cosmology. This is the Hubble tension. There are two measured values for the expansion rate of the universe, and we don't know which one is correct or where the error lies. The name Hubble tension comes from the Hubble constant, represented by the symbol H0, which determines the universe's expansion. To better understand this conflict between possible speeds for the expansion of the universe, we need to understand how we discovered that the universe was expanding.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
We go back to the 1920s. In that decade, two astronomers, Edwin Hubble and Knut Landmark, were independently studying the lights of distant galaxies, and both noticed the same strange phenomenon. All the distant galaxies were moving away from us. And not only that, the farther the galaxy was, the faster it was moving away from our galaxy. This pattern couldn't be a coincidence, and it wasn't. Observations of distant galaxies led to a new view of the universe. Our universe was expanding. Distant galaxies were being pushed away from us by this expansion, and the farther the galaxy, the longer it had been accelerated away by the expansion of the universe. What remained was to determine how fast the universe was expanding. And to do this, we essentially need two pieces of information. The first is how far the galaxies are from us, and the second is the speed of these galaxies. So let's start with distance. To measure distances on astronomical scales, we need astronomical objects called standard candles. A standard candle emits a well-determined amount of light. An example of a standard candle is type 1a supernovae. These supernovas occur in systems with two stars. One of the stars is a regular star, and the second is a type of stellar remnant called a white dwarf. White dwarfs have burned all their nuclear fusion fuel, keeping them stable, and now they are supported by the repulsion between electrons. This repulsion prevents them from collapsing into a black hole. What the white dwarf ends up doing is stealing mass from its stellar companion. However, this additional mass increases the gravity around the white dwarf, and by gaining too much mass, the white dwarf becomes unstable and explodes in a supernova, which is a very energetic stellar explosion. The crucial point here is the following. The mass required to explode a white dwarf is always essentially the same for all white dwarfs. This type of supernova always emits the same amount of light every time. In other words, type 1a supernovae at 1 million light-years or 1 billion light-years emit the exact same amount of light. What changes is how much of that light reaches Earth. So the idea is that by knowing how much light was originally emitted from the explosion and how much light reached us on Earth, we can determine the distance to the star that exploded and consequently determine the distance to the galaxy where that star resided. I just think it's important to say that supernovae of this type are not the only standard candles used by modern astronomy. But the idea behind the method for measuring distances remains the same. With the distance to a galaxy determined using a standard candle, all that remains is to find out the galaxy's velocity. And for that, we need a fact that comes from Einstein's theory of relativity. The color of the emitted light depends on the relative velocity of the object emitting the light. And to understand this, imagine a perfectly ideal star emitting perfectly white light. If this star starts moving away from us very quickly, its light will indeed become more red. This is indeed called redshift, and if it moves towards us, it will become bluer, and that is called blue shift. The effect of this redshift is small, even for objects with astronomical velocities, but it is possible to measure it precisely. Stars are balls of hot hydrogen, and we know well what type of light hydrogen emits. By comparing the light from stars in distant galaxies with the ideal light of hydrogen, we can measure the redshift of the galaxies. And the redshift tells us the speed of the galaxies. So by knowing the position using standard candles and the speed using redshift, we can see the relationship between the galaxy's distance and its recession velocity. And the result is a straight line. The increase in recession velocity is proportional to the distance. In other words, galaxies that are twice as far from us tend to move away from us twice as fast. And the constant that relates the speed of recession to distance is called the Hubble constant, which is known as our H0. And using this method of distances and velocities, the Hubble constant has a value of 73 kilometers per second per megaparsec. A megaparsec is a measure of astronomical distance, and it is equivalent to approximately 3 million light-years. 73 kilometers per second per megaparsec means that two objects 1 megaparsec apart are moving away from each other at a speed of 73 kilometers per second due to the expansion of the universe. And this value of approximately 73 kilometers per second per megaparsec is the first possible measure for the expansion rate of the universe, half of the Hubble tension. The full tension arises when we try to measure this same value using other methods, which instead of using information about galaxies, use information from the early universe. The Hubble tension began when the Planck Space Telescope made the most precise measurements to date of the cosmic microwave background, or CMB. The CMB is the light that was emitted when the universe cooled enough for the first hydrogen atoms to form. The universe was opaque and light couldn't travel without being absorbed by matter. After atoms formed, the universe became transparent. And the light from that moment, 380,000 years after the beginning of the universe, is still reaching our telescopes, bringing information from the distant past. The cosmic microwave background is what you would see in the night sky if you were able to see light in the microwave wavelength. A curious detail is all the light from the cosmic microwave background has essentially the same color. All the cosmic microwave background radiation has almost the same temperature of 2.7 Kelvin. The temperature fluctuations you see represented in this map of the cosmic microwave background represent very small variations of less than 0.01 degrees. These variations seem random, and the pattern is indeed as random as it gets. But this randomness has been created by physical effects that we can try to understand and describe with physical theories. One way to test theories about the universe and its evolution is to ask whether the theory can explain the appearance of the cosmic microwave background. And one of our best theories for the history of the universe is called lambda CDM, which attempts to model from the primordial universe to the way it looks today. This model describes the primordial universe as a soup in which the ingredients are as follows. Particles of matter that make up the atoms that form us. Radiation in the form of extremely high-energy light. And dark matter, which is a type of matter not yet well understood and only interacts through gravity. In fact, the CDM in the name stands for cold dark matter, which is precisely the name for this type of dark matter. And finally, the letter lambda represents dark energy, linked to the accelerated expansion of the universe, and is another great mystery of modern physics. Even without understanding exactly what dark energy and dark matter are, the lambda CDM model makes an educated guess based on what we know and tries to describe the universe from that primordial soup. The model is excellent at explaining various phenomena in the history of the universe, such as the formation of galaxies and other structures. Most importantly, it makes good predictions about the pattern of temperature variation in the cosmic microwave background radiation. According to models like lambda CDM, the temperature fluctuations in the cosmic microwave background radiation have three main origins. Shock waves in the primordial plasma, low-density regions caused by radiation winds, and the transition from an opaque universe to a transparent universe didn't happen simultaneously throughout the entire universe. And each phenomenon should generate disturbances of various sizes and intensities in cosmic microwave background radiation. But not only that, the size of these perturbations is associated both with the speed of these effects and with how fast the universe was expanding. For example, if the universe expands too quickly, matter will soon be too far apart for shock waves to affect very large regions. By measuring temperature fluctuations in the CMB and using a model to estimate how these fluctuations were created, we can obtain a value for the Hubble constant H0. And this value is approximately 67.7 kilometers per second per megaparsec, which is about 10% lower than the value measured using standard candles. But what I want you to understand is that H0 has to be a constant. It cannot have two values, essentially. The first thing to consider here is whether there is something wrong with one of the two ways of measuring this value. Since the first time this discrepancy in values emerged, these two methods of measuring the Hubble constant have been scrutinized in their smallest details. Initially, an error in one of the measurements seemed most likely, but as more data was obtained, the precision of the measurements increased, and it became increasingly unlikely that the Hubble tension was the result of a poorly done measurement. Not only that, but H0 has been measured in even more ways, and these new measurements have also replicated the Hubble tension. In other words, measurements of H0 that use information from the modern universe, such as standard candles and galaxy movements, agree with the value of 73 kilometers per second per megaparsec. Now, measurements of H0 that use information about the primordial universe, such as using the cosmic microwave background radiation, agree with the value of 67.7 kilometers per second per megaparsec. And all of this leads us to conclude that yes, there is a real discrepancy between the measurements. Something truly strange. And not just an experimental error. In fact, in the current scenario, multiple errors in multiple experiments would be needed to explain the Hubble tension. That is practically impossible. We can rule it out. But then, a situation arises. If the error is not in the experiments, it must be in our physical theories. The two ways of measuring the Hubble constant depend on very different physical theories. Measurements using the current universe with galaxies depend on our understanding of stars and galaxies. Measurements using the primordial universe rely on our models for the primordial universe based on quantum physics. Either our models of supernova stars and galaxy movement need to be revised and improved, or our models of any aspect of the primordial universe need to be improved. And not just improved, we need some kind of new physics that has never been thought of before to solve the problem. The Hubble tension represents such a significant mystery that it may be necessary to modify both types of theory to explain the discrepancy, which is excellent. The advancement of science depends on us finding flaws in our theories, and the Hubble tension represents a flaw in our most fundamental theories of the universe. If the measurements of the Hubble constant based on the local universe are wrong, then we need to modify our best models of how stars work. This might open doors to grasp supernovas, white dwarfs, and various astronomical objects. If the problem lies in the measurements of the Hubble constant from the primordial universe, it means that something is missing in our recipe for the universe. Perhaps dark energy behaves differently in different eras of the universe, or maybe dark matter has a more complicated behavior that we do not yet understand. Perhaps, who knows, there might be a new type of matter yet to be discovered. The Hubble tension could very well revolutionize our understanding of the universe. Maybe we are on the brink of a new cosmological revolution, just as when Edwin Hubble discovered the expansion of the universe. And it's wonderful to be sharing this time with you. It's a great time to be alive. Thank you very much, and see you next time.